So now let's give the more formal proof of Fermat's little theorem. And the argument of the proof is going to be essentially exactly as happened in the case on the last slide, where we took the prime P to be 7, and we took A to be the number 4, and we proved that 4 to the power 6 is congruent to 1, I've abbreviated to equal to 1, modulo P. So, as usual, when you're writing a proof, we also will take this as a little bit of a practice in setting a proof out fairly carefully. We write down the information we're given, assume P is a prime, A is a positive integer. That's not said here in the statement of the theorem, but it's implicit that it is, that A is a positive integer, and that P does not divide A. Now, because P does not divide A, well, we know that any A modulo P is going to be equivalent to something in the range 0 up to P minus 1. But because P does not divide A, that means A is not congruent to 0. It's not a multiple of P. So A must lie in the range 1 to up to P minus 1. So we know that A is in this range. And then, by the multiplicative inverses theorem, which I've repeated here, if n is bigger than or equal to 2, and n in this case is the prime P, and A is some number between 1 and n minus 1, so in this case between 1 and P minus 1, and the greatest common divisor of A and n is equal to 1, so A and n have no factors in common, which because P is a prime is the same as saying that P doesn't divide A. So in the particular case, the multiplicative inverses theorem where n is prime, this condition here is automatic in the situation of our theorem. And then we have that these numbers here are a permutation of 1 up to n minus 1. Now it's going to be, instead of using multiplication modulo n or modulo P, it's going to be more convenient here just to write that sequence down here this way. So instead of, well, we have A, and then instead of A times 2 modulo n, we just have 2A reduced modulo n or modulo P. This is ordinary multiplication. Everything's reduced mod P. So we have A, 2A, 3A up to P minus 1 times A modulo P. And that, by the multiplicative inverses theorem, is a permutation of 1 up to P minus 1. This is exactly what happened before when we took A to be 4 and we took P to be 7. So now, multiplying these numbers and these, then we must get that this product is congruent to this modulo P. Because remember that we're not actually taking these numbers, we're taking the remainder of those numbers after dividing by P. We're taking the modulo P. So we can certainly multiply these and multiply that and we get the same answer, modulo P. That's this line here. Now writing that out again more simply, we have P minus 1 factorial times A to the P minus 1, because the number of A's here is 1A, 2A's, 3A's, in fact, P minus 1A's. And on this side here we have P minus 1 factorial, and the numbers here in front, 1 times 2 times 3 up to P minus 1, give me P minus 1 factorial. So that is congruent to P minus 1 factorial modulo P, which means that P divides the difference of the left-hand side and the right-hand side, which is A to the P minus 1 times P minus 1 factorial. But P, being prime, is certainly not a factor of P minus 1 factorial. So that means that, and therefore P cannot divide P minus 1 factorial. So P must divide A to the P minus 1, which just means that A to the P minus 1 is congruent to 1 modulo P. And that completes the proof. There's another way of writing Fermat's little theorem, which you will often see. Although it may look more general, it's actually an immediate consequence of what we have just done. And here it is, that suppose that p is prime and a is a positive integer, then a to the p minus 1 is congruent to 1 modulo p if p doesn't divide a, and that's what we just proved. And it's congruent to 0 if p does divide a, but of course that's immediate, because if p divides a, then a is congruent to 0 modulo p, and a to the p minus 1 will be congruent to 0 modulo p. It also follows that a to the p will be congruent to a. So again, if p does not divide a, then from here we multiply both sides by a, and we get a to the p is congruent to a. And on the other hand, if p does divide a, then both sides are congruent to 0 and hence congruent to one another.